Hello everyone and welcome back to SVSU's online tutoring. My name is Joel and today we will be going over section 7.5 radical equations and applications, and the topic will be applications. So now we've seen quite a bit of radical exponents, radical equations, dealing with graphs and the like, but now radical equations also appear in nature too. So one equation that we can borrow from physics, right, is the amount of power that's consumed by some electrical device, and that's given by I, which is equal to the square root of P divided by R. Okay, and I'll just go through real quick and define each of these things. So I is the current, which is measured in amps, okay? And the symbol for that is A. So let me fix that A, because that's a terrible A, okay? And then R is the resistance within that device, and that's measured in ohms. And then we have our Greek letter here. And then finally, P is our power, which is measured in watts. And the symbol for that is just W, okay? Now, suppose that with some electrical device, it requires a current of 10 amps, okay? And the resistance within that device is 5 ohms, okay? And I want to know how much power is being consumed with this device, so I have to find out what that is. Well, all I have to do is just actually there are two ways to solve this. One way is just by plugging in everything that we know, right? So P square root of P over R, I know that I is equal to 10, and then P divided by 5. So all I have to do here is, let's see if I draw the arrow here, I can break apart this fraction just like that, and so I would multiply the square root of 5 over. So I have 10 times the square root of 5, which is equal to the square root of P. And then I have to square both sides, okay? And the reason for that is I'm trying to solve for P. So I'm trying to solve for the power, right? So I have to get rid of that radical sign. So square both sides. And using our rules that we've learned before, this is equal to P. So 10 squared is 100, and then the square root cancels out with the 2 here, right? So I'm just left with times 5. And make sure that, yeah, so that they're being multiplied. So 100 times 5 is 500. And so the amount of power that I use is 500 watts. The second way to solve this is to just take our equation and then just solve for P algebraically and then substitute. So I have to get rid of this this radical, so I have to square both sides, right? So I have, whoops, I have I squared is equal to P divided by R, and then I multiply R over, and so I get P is equal to I squared times R, and then I just substitute my values. So I have 10 squared times 5, which is 100 times 5. And I end up with the exact same answer as before. So the second thing that we can look at are triangles again. And if we create a slightly more in-depth or real-world type of example, if I have some house over here and it's on some island, let's see, I can maybe draw some water here too. There we go. Here's my water. Draw some grass. Draw some grass. So we got some grass here, okay. And on the second island, so here's our second island. Let's draw some more water here. There we go. And draw some more grass, because why not? So we have this island with a house on it, and then across from that house there's another house, and then over here is the hospital. Okay, so let's draw the nice plus. There we go, for the hospital. Okay, and these three buildings are arranged in such a way that they create a right triangle. Imagine that. So there we, oops, and I cannot draw. So if I have, let's do the diagonal first. There we go. Okay, so just imagine that that's the right triangle. Oh, and the corner of the house there indicates it too. So I don't even have to draw the right angle symbol. Okay, and then suppose the distance between this house on the lone island and the hospital is 130 feet. Okay, and then the distance between the hospital and the same island, or the hospital and the house that are on the same island, is 120 feet. Okay. We want to find out what the distance between the two houses are. Okay, so we're just going to label that B. Okay. So if you recall back, there's a handy-dandy theorem that we can use, and that's the Pythagorean theorem, which is c squared is equal to a squared plus b squared. And this time, right, we're trying to solve for b. So what we can do is that we can simply substitute our values in. So we have 130 squared is equal to 120 squared plus b squared. And 130 squared is 16,900, and 120 squared is 14,400 plus b squared. And then since we're solving for b squared, we want to subtract 14,400 on both sides. So go ahead and show that. And that leaves us with b squared being equal to 2,500. And now what we have to do is that we have to take the square root of both sides. And when we're doing that, right, because n is even, we have two solutions. Okay, so b is equal to plus or minus 50. Now, is it possible for us to have a negative answer? Well, we're dealing with feet here, right? So is it possible for us to have a negative distance? No, it isn't. So instead, what we do is that we reject the negative answer, and then we just say that the distance between the two houses is then 50 feet. Okay. So that's one way of solving this. The second way is to go about it algebraically and solve for b squared right from the start. So again, we have our Pythagorean theorem. And what I'm going to do is I'm going to subtract the a squared this time. And so I have b squared is equal to c squared minus a squared. And then I take the square root of both sides. So I have b is equal to plus or minus the square root of c squared minus a squared, okay? And then, again, I just substituted my values. So I have 130 squared minus 120 squared, and that will be, their difference will be 2,500. And then once again, I just reject the negative root because I cannot have a negative distance. So my final answer is positive 50 feet, which is the distance between the two houses. Okay, that wraps it up for this topic. In the next video, we will begin with section 7.6, complex numbers. So that's really where this chapter picks up and ends on, which is good because that's honestly the most interesting part of this chapter. Okay, see you next time.